Unit 2, Kinematic. Denavit Hartenberg, Homogeneous Transform Metric for Dynamics. Today we are going to talk about Denavit Hartenberg method. Objective. We'll talk about robot serial manipulator, singularity, Denavit Hartenberg method, and Denavit Hartenberg metric. And we'll talk about the design of Denavit Hartenberg rules, creation of the DH table, and the creation of DH metric in Python, and calculate the point position using DHTM metric, Denavit Hartenberg homogeneous transformation metric. Section 1. Robot serial manipulator. Robot serial manipulators. Serial manipulators are the most common industrial robots, and they are designed as a series of links connected by the motor actuated joints that are extended from a base to an end effector. Often they have an anthropomorphic arm structure described as having a shoulder, elbow, and a wrist. Serial robot usually has 6 joints, 6 degrees of freedom, because it requires at least 6 degrees of freedom to place a manipulated object in the arbitrary position and orientation in the workspace of the robot. A popular application for serial robot in today's industry is the pick and place assembly robot called SCARA robot, which has 4 degrees of freedom. So basically, serial robot is a primary, and they are SCARA robot that is a simplified version. Serial manipulator is a human arm-like robot, and we can have a SCARA robot as a simplified version, and it is popularly used. So this one, you can look at it. It is a serial robot manipulator, 6 degrees of freedom. Kinematic. The position and orientation of a robot end effector are derived from joint positions by means of a geometric model of the robot arm. So basically, we can actually use a geometrical model. That's what we are doing right now. We actually formulate it by angles, by link lengths, by its transformation. A serial robot that mapping from joint position to end effector is easy. The inverse mapping is more difficult because of the degree of freedom. Sometimes you may not end up with only one solution, maybe multiple. So here, the calculation is difficult. Also, the algorithm is hard to find a systematic way to do it. Therefore, most industrial robots have special design that reduce the complexity of the inverse mappings. So trying to reduce the complexity, and then you can increase the accuracy of the algorithm. Workspace. So design of the robot, basically you need to take care of the degree of freedom so that you can have good manipulation. Then you need to know about its workspace. So the workspace actually defines how far the robot can reach and how can it pick up something and place to somewhere. So the texturous workspace consists of the points of the reachable workspace where robot can generate velocity that span the complete tangent space at the point. It can translate the manipulated object with 3 degrees of freedom and rotate the object with 3 degrees of rotation freedom. So basically, workspace is very important. It represents how much the robot can help you. And we do modeling, so we need to care about the workspace. We need to care about where it can reach. We need to care about how to model a robot. So workspace, the relationship between joint space and Cartesian space coordinates of the object held by the robot are in general multiple valued. The same pose can be reached by the serial arm in different ways. So they may not be only one set of joint variable that can actually set the value to reach the point, each with different set of joint coordinates. So there are some trajectory planning issues to be done. Hence, the reachable workspace of the robot is divided in configurations, also called assembly mode, in which the kinematic relationship are locally one-to-one. So you can configure the robot into different configurations and you try to operate it in one of them. Then you can reach the target location in a one-to-one mapping format. Singularity. A singularity is a configuration of serial manipulator in which the joint parameter no longer completely define the position and orientation of the end effector. So singularity means that you find certain point that your position and orientation of the end effector can no longer be completely defined. So you may not be able to work out the requirement. Singularity occurs in configurations when joint axes align in a way that reduces the ability of the arm to position the end effector. So you may end up not able to perform some action because your planning is wrong. For example, when the serial manipulator is fully extended, it is in what is known the boundary singularity. So you have the full length on each section and you are not able to actually perform any other thing. So there is no more degree of freedom. So basically you have a base, you have a one link, two link, three link, and you are trying to actually reach this line. So basically you cannot play around any theta at all, except for the base one. Only the base one's theta you can change, you can rotate this one. Other one, you actually, if you rotate, you can never reach this point because you need a total length to reach the point. This we call it boundary singularity. At the singularity, the end effector loses one or more degree of the twist freedom. Serial robots with less than 6 independent joints are always singular in the sense of which they can never span six-dimensional twist space. This is called the architectural singularity. By the design of the robot architecture, you are not able to perform something. So you don't get whatever you want to have. So you don't have XYZ, you don't have the roll, pitch, and weight. So those 6 degrees of freedom is very important. A singularity is usually not an isolated point in the workspace of the robot, but a sub-manifold. So here, let's assume that we have a robot. You try to reach something and your robot arm turn to a certain angle. So you find out that you are not able to reach the target you want to fetch. So you have a singularity. The solution is that you can reposition your robot and then give it a new way to reach the point. And thus, robot should be able to reach the target with the new route. Denavit, Hartenberg. Now, we know the purpose of having a serial robot and the degree of freedom and the workspace and how to reach things. Now, we want to have a systematic way to program your robot so that you can perform a serial operation to reach the target. And the mathematical model is not enough. You need to put them into a program. So Denavit Hartenberg method is the mathematical model that will lead you to development of the robot algorithm. So a homogeneous transformation metric, it can be written like this. You have a rotational metric, a displacement vector, and a 1. And we write down like this. And we talk about this homogeneous transform metric in the previous lab. So now we are going to have a systematic way of developing the Denavit Hartenberg method and metrics. So first, we need to have rules. So there are 4 steps. First, we need to assign frame according to the 4 Denavit Hartenberg rules. There are 4 rules. And then second step, create the Denavit Hartenberg parameter table. So from the rule, we set up the frames and then we collect the parameter. And then we use those parameters to build a homogeneous transformation metric. And that metric can be put into computer and perform calculation, and we can multiply the matrix together to form a bigger combination of the transformation matrix. Denavit Hartenberg frame. So the duo, we need to design the frame in a way so that it can help us to design a better way to model the workspace. As we say, with this better way of modeling, we will actually be able to systematically set up a good way to reach the target. So you must have at least one more frame, then they are joined. So if you have 3 joints, you may need to have 4 frames. And then 1 frame must be the end effector. So end effector take 1, and usually 3 joint takes 3. Now, all axes must be drawn either up, down, right, left, or in the first or third quadrant. So we don't like the drawing like this. We don't like this kind of situation in the second quadrant or fourth quadrant. We like it to be first quadrant or third quadrant. So that gives us better idea, because in the second quadrant, the angle is too small. Usually not easy to find a good model. Now, 4 rules for Denavit Hartenberg frame rules. Number 1, the z-axis must be the axis of revolution or the direction of the motion. So basically, z-axis is used for rotational axis. Or if you have extension, z is used to here. Then second one, we have x direction. X direction will be kept to be perpendicular to it. So basically, you can be here, you can be here. And then one more thing is that if we have 2 frames, here we set up x, this x must not be perpendicular to the previous frame. That's the rule number 3. Number 4, if you have a y, you actually want to do right-hand rule. So basically, you have a sum over here, and your palm like this, you will go this way. So the y actually should be this way, and then you can rotate this way. Use the right-hand rule. The right-hand rule is popularly used in physics for cross products. Now, here we have 3 joint, 4 frame, 3 degree of freedom robot. And rule number 1, we set up the z direction, and we find this direction for G0, G1, G2, G3. And as you can see, for the joint, the G pointing to the direction that you have the revolution as the exit, central exit, or you have the G direction for its motion, the extension portion. And G3 is the end effector, so we follow the G2. Rule number 2 and number 3, you set up the X. Here you need to take care of the basic rule. Number 1, it must be perpendicular to its own G. Second, this X can never be parallel to the previous G. So here you have the X, and this one actually is, this one is X, it actually is perpendicular to it. This one has X, it actually is perpendicular to this one. And X2 also perpendicular to G1. So this is okay. But this one we'll simplify a little bit later. Then Y dual, you actually use a right-hand dual to determine the right direction. So now here is a block model for this robot. Denavit Hartenberg parameter table. Now here comes the most typical part for Denavit Hartenberg parameter table. So you have 3 frames, and you should have 2 rows. 4 frames, 3 rows, because each row represents the relationship between 2 frames. So it is used to model the so-called homogeneous transformation matrix. So basically, this one is H01, this one is H12, and then if you have third frame, it will be H23. So totally we have 4 frames, 3 rule over here, 3 lines in this table. And then it will be used to generate 3 different matrices. That's number 1. Second, we have X direction revolve angle Z direction without angle, X direction movement, and Z direction movement, 4 different parameters. And X direction angle, we call it theta. Z direction angle, we call it alpha. X direction movement, we call it R. Z direction movement, we call it D. But don't get confused with your own parameters. They are different. These different parameters used for Denavit Hartenberg parameter table. Sometimes the R is also using A, but you have to check out the different system when you work on homework or different model. So here is a model for the robot when we actually make little bit transformation. So here actually originally you have your D2 over here, S2 over here, Y2 over here. We move to here because it doesn't matter. The extension portion is over here, and we move it here. We actually can make the table easier to do. And also on your Z direction, we actually set the Y to facing this way instead of facing this way. The reason has been that we actually may have possibility of extending it here in the future. So now first one, X revolution angle theta. So basically this theta, it is the frame 0 to frame 1. So you want to determine your frame 1. So it's determined by the S1 and S0. So how to determine it? It actually is what? You basically have two components. The first component is the angle of moving your x0 to the s1 direction. And your x0 right now is this direction. S1 is this direction. So basically, you kind of have the same direction. So the theta actually is 0. And you also need to add the rotational matrix theta 1 here. For example, if this one move a theta 1, and then your x1 move to this direction, so your x need to, at this time, need to catch up. This is theta 1. So this theta 1 should be put here if there's a rotation of theta 1. So this theta is the difference between your x0 and s1. How much you need to catch up by your x0 to s1. So by doing that, you know that this theta for h01, it will be theta plus 0 degree. Second one, you have your s1 over here, your s2 over here. So s1 rotate to s2, you need to take angle like this. It will be 90 degree. So basically, that is 90 degree. And then if your theta 2 also turn, your theta 2 also turn, then your x2 may turn an angle like this. So there is a theta 2 you need to catch up. So that's 90 degree plus theta 2. And then we look at frame 3 versus frame 2. Frame 3, your x direction, x3 is here. Your x2 is actually here. So you need to turn the angle from here to here. So basically that will be from x2 to x3. So it's turning this way. So it's a 90 degree. Your z direction, z2 direction, your z2 direction is over here. Your z2 direction is over here. Based on right hand rule, you will turn like this. But there is no theta 1 or theta 2 involved. So that's the first x revolution angle theta. Then we check the z revolution angle theta. So z revolution angle theta, we actually using the z0 pointing to here, z1 pointing to here, and then with respect to s1. This one must remember is with respect to s1. Because your s1 change, it may change. Okay. So here, for example, right here, the two have an angle of this z0 catch up to this one, it is 90 degree. And then when you see that move, when you see that one move, you see that one move, your basically your z0 not changing, and then your z1 actually will keep moving to a certain direction, and it actually is something that is in this direction. So basically, it's still a 90 degree turn from here to here. So it's always 90 degrees. And then let's check the friend 2 and friend 1. So friend 2, your G direction, friend 2 direction is like here. The D direction here is like here. So you basically need to turn this based on your S2. So here, because your S2 is up, your right hand rule is still 90 degrees. And the next one is your D3 versus D2. D3 versus D2, they are same direction, so you put a 0 over there. This is the so-called G revolution angle alpha. So X for theta, D for alpha, and then X for R, D for D, okay? So third one is actually X movement. X movement, you have the R, and this R actually is the movement of the F0 to F1 in X1 direction. So here, X1 direction here, it will be this direction. Your X0 is over here, and moving in that direction to your S1. Your S1 actually is over here. So it actually need to catch up this much. So it is A2. Okay? And then next one, your friend 1 to friend 2. Friend 1 to friend 2. Your friend 1, the center is here. Friend 2, center is over here. You don't need to move, so it's 0. Friend 3 to friend 2, actually friend 2 to friend 3. Friend 2 is over here, friend 3 is over here. And it needs to be in the S3 direction, and S3 direction, actually the two are same value, so 0. And the last one is D. D actually is the G axis and based on G minus 1. So let's look at this one. So first one, we actually have your G over here, it's over here, and here is over here, and it actually in G n minus 1, so N G n 0. So here it actually should be going up by A1. So this one is A1. And then second one, you have two are same points, so it is the same. Third one, the G direction is here, and original is over here, and it's in the direction of the D. Let me see, it actually should be G2. G2 is over here. D2 is over here, so basically you need to have A3 plus A4 plus extension D. Now, let's look at how this table is useful in the Denavit Hartenberg homogeneous transformation matrix. So the rule is very simple. You've got a row, and that row say is Hn minus 1 to n, and you just perform this matrix. Put the number of theta n, alpha n, Rn, and Dn into it. So basically, pretty mechanical operation. You can create this. And in Python, we will have a function to create such a matrix. So it's not hard. So here, let's see, we have row 1 generate H01, and row 2 generate H12, and row 3 generate H23. And with these, we can combine and calculate the H03. And let's look at the Python code. So here, Python code, we actually have a function called dh underline htm. You take in theta, alpha for AF, R with RD as D. So here we actually put in all the numbers theta, alpha, R, and D into here and calculate for a matrix called D. And this one actually is the same as same as this one, and it is the implementation for this metric in this page. So that is the Python code we have. And then before we work on it, we should put the number of theta 1, theta 2, and D, and also the A1, A2, A3, A4 to here. So D, I assume 0, A1, A2, A3, A4 as 1, and then theta 1 90 degrees, theta 2 0. That is one of the set you can do. You can actually change the value over here. And then with that set of the data, we generate H01, H12, H23, and H03. H03 is the multiplication of these three matrices. And then if we have a point that's called 0, 0, 0, that actually is when we have a notation like this, we have this one like this, we have an extender over here, and effector over here. So this one, 1, 1, 1, this one from here to here, also 1, and here we have theta over here, theta 1, we have theta over here, that's a theta 2, okay? So with this parameter, and then this one point is 0, 0, 0 with respect to frame 3. So if we make a 90-degree turn, and then this space not moving, and then actually this 1, 2, 3, it will move up to 3 here. So basically it become here x is 0, g actually is 1, y is 3. So we end up with x equals 0, y equals 3, g equals 1. And that actually is the W times the Denavit Hartenberg matrix will give you the W0 with respect, and this W is the coordinate versus the with respect to frame 3. And this 0n is the coordinate of that point with respect to the base coordinate point in the frame 0. So this actually show you that the data is correct. Let's look at the Python code in PyCharm. So here we have the Python code like this. Okay, so we have import the numpy, and we set the error label to be 10 digit. Okay, and here we have a Denavit Hartenberg homogeneous transformation matrix creator, and you give me theta, alpha, R, and D. And display, you can set true or false. True means that you are going to print the matrix out. False, you will not. And then name, you can change the name for your matrix. And here I set it to be dh_html as default. So this few array, it is actually creating the matrix arrays, and you create a 0 using numpy zeros 4, 4, that create a 4x4 matrix of 0, and then you fill in the data over here. So here initially the robot parameter we have degree 90, that's actually convert the 90 into the radian scale. Same thing for 45 degree, and then we assign 90 degree to theta 1, theta 2 as 0, okay, and 1, 2, 3, 4, and D no extension. And then this different number, theta 1, theta 2, A1, A2, A3, A4, we put into a Denavit Hartenberg table, and that table with theta 1, theta 2, theta 3, this is row 1, row 2, row 3 is the theta, alpha, R, and D. So these are the table. This is the table. I put them into such a format. And then I put in the value for testing, and that one actually initially I do not have any value for the theta, for the alpha, everything is 0, everything no move. And then I put a 90 degree to the theta, and then alpha and the R and D are 1 and 1, okay? And the third test, I have 45 degrees. Let's look at these three tests first. So I have run the result. So let's see here. I have run the result, and let's see. No move, 90 degree. Okay, so the first one, no move. No move when I put all the 0 over there, and according to our matrix formula, I have everything 0. So cosine is 0, cosine 0 is 1, and sine 0 is 0. So here I end up with only diagonal term. So basically this is identity matrix, and it do nothing. Okay, that's no move. and R is 0, D is 0, so these three terms are 0. Sine, anything with sine term are actually 0, so you only have a diagonal term, that's noble. Second one, you do 90-degree turn. 90-degree turn, let's look at it. You do 90-degree turn on theta. So this one actually is a model of a single rotator like this, and you have A1, A2, right? And your endpoint is over here, and it turn 90 degrees, so you should turn to here. So second one, 90 degree, the sine, cosine, the rotational metric over here show up very clearly. It is a 90-degree turn for X and Y, but Z no move. And then original point is 0, 0 over here. The end point here is G1, Y also 1. So you got 1, 1 over here. So next one, if we turn only 45 degree, the third metric, if we only turn 45 degree, we end up with a rotational joint like here. It actually original is here, and effector, and we turn 45 degree over here. So basically, your G is 1, and then here 45 degrees. So here is square root of 2 over 2, square root of 2 over 2. So we end up with this different value. And then the rotational metric is like this, D no move. And here we have cosine 45 degree minus sine 45 degree, sine 45 degree, and cosine 45 degrees. So we end up with such a metric. So these three testing actually pass. Now let's look at the next one. So we test our metric creator with these three basic ones. And then we use the table value here, put into my creator and generate 0, 1, 1, 2, 2, 3. And then using 0, 1, and 1, 2 generate 0, 2. And using 0, 2, and 2, 3, we generate 0, 3. Okay, we generate 0, 3. And then we actually kind of round in the 0, 3. So that is our N metric. And we create a point that's actually coordinate 0, 0, 0. Put a 1, that 1 actually is for the so-called vector, the vector that we use to put into our homogeneous transformation metric, okay? And we actually convert that to a 4, 1, it's a column vector, and we time 0, 1 with that column vector. We will create the first joint operation, and then here second joint operation, and this one third joint operation. So that we end up with here. So here is 3 number. So let's look at the result. Our robot is like this. So here it's 1, 1, 1, 1. And then first joint, you turn 90 degrees. So turn 90 degrees. First joint, move to here. So it become Z equals 1, Y equals 1. Then this second friend 2, is also the same value because we overlap the 2 friends in the same location, even though they are different orientation. And then your last point over here, it turns 90 degrees to here. So actually is Y equals 3, Z equals 1. Okay, so basically this set of data is correct. We actually show you how to build the Denavit Hartenberg homogeneous transform metric, and also plug in real value to verify our metric. And this whole thing can generate a very solid algorithm for the generation of the metric transformation metric, and it can be used in many applications for the calculation of kinematics. You can use the metric to create instantaneous move. Say your W, you can use delta P, tiny change of the P. Then you actually can use that one to create its tiny change in the past. Okay? Thank you. Bye now.